properties of continuous functions. So we're gonna have a few theorems today and in the coming classes. I'll prove some of them along the way. I won't prove all of them. Many of the proofs are also in your book, so you can certainly read those if you don't believe me. So one is that once we have continuous functions, we can take them and start combining them in different ways to create new continuous functions. Okay, so first result is that if f and g are continuous, okay, on a set S, right, then we can add them, we can subtract them, we can multiply them, and get new continuous functions. So then we can say, so are f plus or minus g and f times g. Okay, and this is something, I'm not going to prove this one. This is something you can check using the definition of continuity. And then what's the result for f divided by g? Sure.
The same when g is not 0.
It's the same as long as g is not equal to 0. So we can say that f over g is continuous at points x naught where g is not equal to 0. Right, and that's not a surprise. We know that we don't want to be dividing by 0. Right, so as a quick example of that, we could take something like, say, x over x squared minus 1. Okay, so we've taken continuous functions and combined them in different ways. Right here, x squared is x times x. That's multiplication. We have subtraction, division of continuous functions. And we can say, great, this is continuous as long as we don't end up with a 0 in the denominator. So this is continuous except at plus or minus 1. Okay, or we could take something like f of x equals x times sine of 1 over x. Okay, and where is this continuous? Where is it not continuous? Let's ask that.
0.
It's not continuous at 0, exactly. So this is discontinuous at x equals 0. For the simple reason that it's actually not defined at x equals 0, and that's all you need to check, right? Continuity, you have to have the limit, you have to have the value, and they better to be equal to each other. Here we don't even have a value, so we're done. Right? So I could say since it's not defined there. Is there a way I could patch it? So if I tried to modify this function a little bit and say, I'll keep the same function wherever it's defined, and I'm going to give it some other value at x equals 0. Okay. Now I can define any function I want like that with any value I care to put here. What value could I put here that would make this a continuous function? Give you just a second to think about it. So what does it mean for a function to be continuous? It means that whatever the value I put here is has to be exactly the same as the limit as x goes to 0. When we're taking limits, we're saying what happens when x is close to 0 but not 0. So the limit of this guy is x goes to 0. This one we've seen 0, exactly. This limit goes to 0. So if we put a 0 here, we're going to say this actually is continuous at x equals 0. Okay, so we can do piecemeal definitions and patch things like this. Okay, and then we can do combinations of functions in more complicated ways. This one I am going to prove. So composition of functions. Okay, so let's say that g is continuous at some point x naught. What I want to do is stick a function inside of another function and try to get something that's continuous. So I'm going to stick this function inside another function f. F is going to be continuous at g of x naught. Okay, then I claim that f of g of x, so this is a new function, that this is also continuous at the point x naught. Right? And to just wave our hands, we say, well, g is continuous at x naught. Then we get a g of x naught here. F is continuous at that point. We get f of g of x naught there. So it's reasonable. It's reasonable that this could be true, that this is continuous at x naught. Okay, so let's see if we can try to prove this. Okay, using our epsilon delta definition of continuity. Right, because, okay, we know one way to do this is to say the limit equals the value. The limit involves already epsilon deltas, so we can use the just straight out epsilon delta definition of continuity. So let's try to do that. Let's choose epsilon greater than 0. Okay, so this step of the proof was easy. This is the first step of almost all the proofs that we do, right? And then we're going to continue the way we always try to continue. We're going to write down the things that we know and try to push towards the thing that we want to know. So things that we know are, well, we know that this function is continuous, and we know that this function is continuous at particular points. Okay? So we're going to write down what that means. Okay, so f is continuous at a point g of x naught. Okay, so what does that mean? That means that for every epsilon greater than 0, say this epsilon, I can find some value of delta, right? I'm going to call it delta 1. Such that let's say that f of t minus, so the value of the function at a generic point minus the value of the function evaluated at this point where we're checking continuity, so minus f of g of x naught, can always be made less than epsilon. Right? As long as the things that we've plugged into here are generic point, we're used to calling it x, I'm calling it t here, minus the point where we're checking continuity, as long as these are within delta 1 of each other. Okay, we agree this is a true statement? Okay, this is continuity. Now I'm also going to write down the fact that g is continuous. So g is continuous at x naught. That means for any number, for my tolerance, right? Usually I'm used to calling my tolerance epsilon, but I could give it a different name. What would I let's just think about this for a little bit. What would I like to call my tolerance here, right? We know that we're going to have g of x minus g of x naught, and that's the thing that we're going to plug into f, right? So it seems reasonable if these are the things we're plugging into f, we'd actually like them to be within delta 1 of each other, right? Because we're going to feed this tolerance into this tolerance into this tolerance. So what I'm going to say is, let's let delta 1 play the role. I write like this, play the role of epsilon in the definition of continuity. Okay. It doesn't matter if I rename things, right? The theorem is true regardless of what I decide to name things in the theorem. The definitions are the same definitions regardless of how I choose to name things. And again, we know there exists some other parameter, delta 2, such that g of x minus g of x naught is less than delta 1, right? So this is playing the usual role that epsilon plays, as long as x minus x naught is less than the tolerance in this direction. Okay, so it's a little bit different than the way I usually write the definition of continuity, only because I've renamed things, because we're used to calling this epsilon. I've just given it a different name, right? Because all that definition says is, for any small tolerance I pick, I've decided to pick the small tolerance delta 1. So we believe that this is true. This is what it means for G to be continuous. Okay, so now we're going to try to put this together. We're going to try to build up the result that we want. Right, so what is the result that we want? We want to be able to say that f of g of x minus f of g of x naught is less than epsilon, right? That would be what it would look like for this function here to be continuous. So this is our goal. So let's choose x such that x minus x naught is less than our delta 2. Okay, all I'm doing is rewriting in a different order the statement here that G is continuous. Right, we know that G of x minus G of x naught is going to be less than delta 1. Again, I can rename things. This condition here, g of x minus g of x naught less than delta 1, looks a whole lot like this condition here, right? Something minus g of x naught is less than delta 1, right? So as long as this is less than delta 1, I can let g of x play the role of t throughout this, right? All this says is that for any number that I have to pick that satisfies this condition is satisfied if I use the same number here. So let's let t equals g of x. Then what we have is we have t minus g of x naught is less than delta 1. Okay, now we go back to the thought that we wrote down f is continuous. We said if t minus g of x naught is less than delta 1, then automatically, right, we have this constraint on how much f can vary. So this means that f of t minus f of g of x naught is less than epsilon. And why does this help? This helps now because I said t and g of x are playing exactly the same role here. They're equal to each other. So this means that f of g of x minus f of g of x naught is less than epsilon whenever we start with x in this little window here. Right, so what have I done? We started by saying, give me any epsilon you like. I don't care how small it is. We can construct this other number, this delta 2, right? So epsilon is usually our tolerance in the y direction. We can construct this tolerance for the x direction so that as long as we're within the tolerance, the value of the function never wanders more than epsilon away from its value at this point where we're checking continuity. All I've written down here is precisely the definition of continuity, or the restatement of the definition of continuity in terms of epsilons and deltas. So this really says that, indeed, f of g of x is continuous at x naught. Yes?
So when evaluating some limits in previous calc courses,
Yes.
we use some sense of composition of limits.
Right.
Does that follow from this, or is that something that...
So that follows from this, right? So with composition of limits, when you're saying, can I take a limit and pass it inside a function? You can if the function is continuous. You know that you're going to get the same, exactly the same value. So yeah, that's exactly where this comes from.
If the function is non-continuous, can you still sometimes do stuff with one-sided limits and things like that?
With one-sided limits, you may have one-sided limits with a non-continuous function. But again, with non-continuous functions, you've got to be a lot more careful. You don't get to just take limits and put them inside the functions. Yeah, good question. Any other questions on this? Right, it's a more technical proof. It's definitely a more technical proof. But I want you to see, it's using the building blocks that we've created here. I haven't tried to do anything very sneaky here. It's really just writing down the things that I know and then seeing if I can manipulate that into the thing I want to know. And this is the thing I want to know. Over here. Okay, so this is powerful. This lets us build up a lot more continuous functions just from some simple basic functions. All right, so for example, f of x equals, let's say, sine of the square root of x plus 1 over x squared plus 1. Right, and now, as long as things behave themselves, right? So here we have, okay, operations of addition, multiplication, division. We have the square root function. So everything is good in here as long as we live within a region where the square root function is continuous. Right? In other words, as long as whatever is happening in here is positive, we're happy. Then we pass all that into the sine function. Sine function is continuous everywhere. It doesn't care what we give it. Right? So this is going to be continuous. Right, as long as x is bigger than minus 1, right? So that we're not taking the square root of a negative. Or equal to minus 1, right? And then for the boundary, we can say, let's look at the one-sided limit, right? And I think Professor Oza talked about that with you probably. If the one-sided limit exists and you get continuity there, then we can even put a equal to there. In other words, this is continuous everywhere in its domain. Okay, so we're happy. You can build up continuous functions. You can verify if they're continuous, and either using the definition of continuity if you're asked to, or by using theorems that we've proved, right? Once we've got a result and we've proved it, it's true and we can use it, right? So I could have checked this using the entire epsilon delta definition of continuity. It would be ugly to try to check this, but in principle you can do this. Or I can say I have some theorems that I've proved once and now I don't have to do the work again. I can just say it. All right, continuous functions have other nice properties. So one is that we can often show that continuous functions, under the right circumstances, stay bounded. They're not allowed to get too large or too negative. So let's define what I mean by bounded, first of all. A function is bounded below on a set S if okay, so to say that something is bounded below, this is going to be very similar to when we were talking about sets being bounded. Just means there's some number down here, wherever it is, such that the function never dips below this number. So if there exists some m, okay, such that f of x is always bigger than or equal to m. Okay, and then we can similarly come up with the concept of a function being bounded above, right? This just means there's some number up here. It might be a big number, I don't know, but there's some number up here that the function never gets to climb above, whatever else it's doing. So, almost the identical definition. A function is bounded above on a set S. Again, if there exists some number, we call capital M. Capital M acts as an upper bound on the function, so such that f always stays less than or equal to capital M. Okay, and we're going to say that a function is just bounded, generically bounded, if it's got a bound from below and a bound from above, if we've got it sandwiched in between two finite numbers. Okay, so this is our last piece of our definition. A function is just straight out bounded if it's bounded above and below. We're happy with this definition? Okay, so why do we care about this right now? We care about this because in the right circumstances, continuous functions are guaranteed to be bounded. Okay, and what are the right circumstances? We're going to say that if f is continuous on a finite closed interval, so a to b, then f is bounded on a to b. Okay, this one I'm not going to prove here. It is in your book. You're welcome to read it. You're welcome to in fact, you're welcome to disbelieve this until you've taken the time to go read the proof. I'm fine with that. I try not to lie to you, but you can always check these things yourself. I think this is theorem 2.2.8. But we'll just write a couple examples of using this, seeing why we need all these conditions, why we need this interval in particular to be finite and closed. Right. And clearly, I think you can think of non-continuous functions that get arbitrarily big. But let's see what else we can come up with. So for example, if I take the function x squared plus 1 on the interval 0, 1, this is indeed bounded. Right, on this interval, the smallest we're ever going to get is f equals 1. The biggest we're ever going to get is f equals 2. Those act as bounds on this function. But we could change things up a little bit. We could say, let's have the same nice function, but now on the interval 0 to infinity, right? So this is still a closed interval, but it's not a finite interval anymore. And if it's not a finite closed interval, our theorem doesn't work, and that means if the hypotheses fail, the conclusion we don't know, right? It could be true, it could be false. We don't know, and in this case it's false, because this is going to get arbitrarily big. So this guy is bounded below still, right? It's the unbounded interval, an infinite interval. We're bounded below, but we're not bounded above. This thing gets arbitrarily big. So this is bounded below, but not above. Okay, and then why does it have to be a closed interval? Well, I'm going to switch up the function for this. And let's take this to be 1 over x on the interval 0 to 1. Okay, I have not included 0 in the domain, right? So we're never in danger of plugging x equals 0 into here. That means we know this function is continuous on the domain that I've given you, right? Because this is just division of two continuous functions. Those are always continuous as long as we're not dividing by 0. So this is certainly continuous. This is certainly a finite interval. It's not a closed interval, and it's not being closed that breaks things. Because while this is continuous, arbitrarily close to x equals 0, we know things would break if we actually let ourselves get to x equals 0. Right? So this is not bounded. It is bounded below. So it is bounded. It is not bounded above, but is bounded below. Shouldn't it be the other way around? Well, as x goes to 0 from the positive side, this is going to approach positive infinity, right? So this thing is going to get arbitrarily large. We can sketch it. All right, so as at x equals 1, or as x is close to 1, this is going to get also close to the value of 1. And then it's going to do this.
So why is it bounded below?
So it's bounded below, right? Because we can put a number down here, right? And the function never drops below this number, right? That's what we said was our definition of bounded below. If I can find a number, so here my number might be 1 or 0 or whatever you like, it's less than that, such that f is always bigger than or equal to that number. So here I could put the number 1 here. F is always bigger than or equal to that number on this interval that I've specified, right? So the domain matters when you make these decisions. Okay, so we have bounds for continuous functions as long as we live on nice intervals. Then the other really nice thing is that we have maxima and minima, right? Now, we've looked at cases for sets where sets might not have a maximum, right? We might have a least upper bound, a supremum, but not actually a maximum. And functions can do the same thing. But if you have a continuous function, again, on a nice interval, a finite closed interval, it's always going to take on a maximum. Okay, so here's another result. This one's pretty useful. I'll say in a lot of applied mathematics, you're setting up problems to minimize different energies or things like that. Nature is always trying to minimize energies, and then the mathematician's job is to say, but actually, is there a minimum or is there not a minimum? And you make a lot of arguments from continuity and things like that to try to say, does this model make sense? Does it not make sense? So again, if f is continuous on a finite closed interval, AB, then these two numbers exist. So the maximum on this interval of f of x and the minimum on this interval of f of x, these numbers both exist. Right? In other words, we have a least upper bound, right? We know we should have a least upper bound because this function is bounded. But not only do we have a least upper bound, we can find a value of x where f is actually equal to that smallest bound, where f is actually equal to its maximum value. We can find a value of x where f is actually equal to its minimum value. Okay, so again, I'm going to do some of these similar examples. F equals x squared plus 1 on the closed interval, 0 to 1. So what's the maximum of f? 2, right. So we can say that the maximum of f is 2. And in order to do that, we have to be able to plug in a value into here. And indeed, we can take a value that lives in the domain and plug it in. Not 2, 1. Let's try 1. OK, but let's change things up a little bit. So I said we need a finite closed interval in order to be guaranteed a maximum. Let's try something that's still finite, but not closed. So I'm going to take the same function on 0 to 1. OK, what's the supremum of f? What's its least upper bound? It's 2 again, right? It's still, as x approaches 1, we're going to get arbitrarily close to the value of 2. So the supremum of f is 2. And what's the maximum of f equal to? It does not exist, right? And the reason it doesn't exist is because I cannot find any value that I can plug into the function that will give me 2, right? Before, in this case, we could say, let's take this value of 1, that lives in the domain, plug it in, and we get 2. Now I can't do that because I would like to grab the value of 1, but it doesn't live in my domain, right? That value doesn't exist to me. So we're going to say, actually, the maximum of f does not exist. Okay, and one other example. I'm going to take this function again, but I'm going to switch up my domain a little bit. So now my domain is not going to get close to 0. I'm just going to go from 1 to infinity. So indeed, this function is actually bounded on this domain, right? We cannot conclude that from this theorem, right? It doesn't fit within the framework of the theorem, but it does happen to be bounded. All right, so now we've got the right-hand part of this function, where it's just going to go from 1 and trail down to 0. So what is the infimum of this function? 0, right? This function, as we head out to infinity, is going to get arbitrarily close to 0, but always stay above 0. So 0 is a bound. And what's its minimum? It also does not exist, because we'll never hit 0, right? I can't take infinity and say, let's plug x equals infinity in here to get 0. Infinity is not a number. It's not a number that lives in our domain. So a minimum of f also does not exist. Any questions on these properties? Right. They're reasonably straightforward properties of continuous functions, but it turns out they're really important properties of continuous functions that we actually use a lot because, again, a lot of applied mathematicians care about existence of minimizers to things. You have particles bouncing around, and they're trying to minimize some energy. And does our model make sense that we actually get a minimum? Okay, then yes.
We were given a problem where we had to prove that a function had a max and a min
Yes.
on an interval. We first have to prove that it was continuous on that interval.
So that's one way that you could do it. You could say, well, this is a continuous function, right?
We have to show that, right?
Well, not necessarily, right? Because now we have theorems about how we can tell if a function is continuous, right? Just like I did for when I had the sine of the square root of whatever. I said I could do a delta epsilon proof, or I could say we've just proved a couple theorems about this. Don't make your life more complicated than it has to be. There will be times I want you to do epsilon delta proofs, and I'll typically tell you what I want you to do, because I want to know that you understand them. But otherwise, you can always use results that we already know, that we've already proved. Mathematicians would not get very far if we weren't allowed to use our earlier results, if everything had to always be proved from scratch every time. Any other questions on this stuff? So one other big property of continuous functions is, it's the intuitive one that you think of, that I can draw this thing without lifting up my pencil, right? In other words, if I started a value here and end at some other value up here, I've passed through every other value along the way, right? Do you remember what that theorem is called? Intermediate value theorem, very good. So we'll write it down. Okay, so this just says exactly what we just said, that a continuous function passes between all values, between its endpoint values. So suppose f is continuous on an interval from a to b, with f of a not equal to f of b. And let's choose any number between these two values. So let's let mu be any real number lying between f of a and f of b. Then the theorem says there exists some c, some other value in our domain, inside our domain, such that f of c is equal to mu. Yes?
This also requires a finite interval, right?
This would, So what would it require? It would require f of a and f of b to be legitimate values, right? So if this was infinity, then no. Now, if you had an unbounded domain, I could just pick something and say, I want to look between f of 0 and f of a googolplex or something, right? I'll pass through every value between those. But yeah, certainly I need these numbers to be well defined. Okay, and I think you know this picture already. So I draw the picture, and here's A, and here's B. Here's f of b. Here's f of a. And I can just pick any value of mu between them that I like. So I'm going to put mu here just because I can. And what this says is if I draw this line at the level of mu across the domain, somewhere we're going to get an intersection point, right? And that's my point C. And this, just make it clear, the shorthand. We're gonna use this theorem again throughout the semester a couple times probably, and I'm not always going to want to write out the whole thing. So this is our IVT. I think, in the interest of time, I'm not going to prove this one on the board. It's an instructive proof. We're going to do other proofs that are very similar to it, and I want to be able to focus some time on proving things about derivatives as well. So it should be in your book. I'll actually check if the proof in the book is nice or not, and if it's not, I'll post a different proof on Moodle. But we're going to do other proofs that use very similar kind of arguments. OK, so we've learned a bit about continuous functions. What's the next obvious thing that we should do if we're doing calculus? Derivatives, sure. OK, so this takes us into 2.3, differentiation. OK, so what is the derivative of a function? You can give me the intuitive hand-waving definition. The slope of the tangent line, sure. OK, so here's f of x. And I'm interested in some point x naught. I draw the tangent line here, and I say f prime of x naught is going to be the slope of the tangent line. OK, that's a little hard to just read off a function immediately, right? So we need some more rigorous definition of this. Well, I mean, what even is a tangent line? So let's put this in terms of things that we can calculate. Tangent lines at this point are hard to calculate because you kind of need a concept of derivative to do it. Secant lines are not so hard to calculate. A secant line just passes through the function at two different points. And this we can do. So let's look at the secant line instead. So here's my function f again. I'm going to look at x naught, which is the point that I care about. And then I'm going to look at some other point, x naught plus h. OK, these values I can get, right, just by plugging into my function. I don't need to know what a derivative is to get at those. And then I can draw a line that connects them. And we have some intuitive idea that the slope of the secant line is pretty close to the slope of this elusive tangent line as long as we've taken these points relatively close together. And that is going to become our definition, really. So the slope of the secant line is close, whatever that means, as long as h is small. Okay, and now we have a robust sort of concept of making things arbitrarily small, right? This is limits, and we know what limits are. So this gives us a really natural definition. The derivative of f at a point x naught is, okay, I'm going to just take the slope of the secant line. Slope of the secant line is nothing but rise over run, right? So f of x naught plus h minus f of x naught divided by the run. And now we try to make h arbitrarily small. So we take the limit as h goes to 0. And we call this f prime. Right? As long as this limit exists. This is our derivative. And I'll write out an alternate way of doing this. Instead of calling this point x naught plus h, I could call this point just a generic x and require x to approach x naught. So sometimes it's easier to do the computations this way. So f of x minus f of x naught, my rise, over my run again. So exactly the same thing. You can use whichever one you prefer or whichever one looks easier. Okay, and if this number happens to exist and to be finite, then we're going to say f is differentiable at this point. So if f prime x naught exists and is finite, then we say f is differentiable at x naught. All right, so what's the link between continuity and differentiability? If I have a continuous function, is it automatically differentiable? No, it's not. All right, so if we're looking for a link between continuity and differentiability, we know the link isn't to say that continuous functions are automatically differentiable. Right, so for example, I could take my absolute value function. Right, so this is continuous. It's either plus x or minus x. But there's no derivative, right? And we can check that there's no derivative. So this is certainly continuous. If we wanted to check if it's differentiable, we'd have to try to see, does this limit exist? Okay, so if I look at f of x minus, say, f of 0 divided by x minus 0, well, there's two things that could happen, right? Either this is equal to x if x is positive, or it's equal to minus x if x is negative. That's how our absolute value function works. So this is either x minus 0 divided by x if x is bigger than or equal to 0, or minus x minus 0 over x if x is negative. All right, and if we simplify this down, this is going to be a 1 if x is positive. It's going to be a minus 1 if x is negative. It's going to be not defined if x is 0. So this, we could say, is 1 if x is positive, and minus 1 if x is negative. Okay, so what's the limit of this as x goes to 0? It doesn't exist, exactly, right? Because as x goes, we have one-sided limits. As x goes to 0 from the positive side, we get 1. As x goes to 0 from the negative side, we get minus 1. But those two things don't match, right? So the limit as x approaches 0 is going to not exist. Therefore, f is not differentiable at this point that we checked at 0. What about the other way around? So we said, we're trying to say, is there some sort of connection between continuity and differentiability? It's clear that we can find continuous functions that are not differentiable. Can we find differentiable functions that are not continuous? What do you think? You think no? Okay, your intuition here is exactly correct. So this is another theorem. If f is differentiable at a point, then it's continuous. So be very careful with this. This is a one-way implication, right? Differentiable implies continuous. You cannot take this in reverse. We just did an example where we showed we cannot take this in reverse. Oh. And somebody will get tripped up on this at every exam, and I'm telling you now, don't get tripped up on this. This is a one-way implication. So let's try to prove this. Okay, so I'm trying to prove this. I'm going to start the way I always start and try to write down what I know. And the one thing that I know is that this function here has a derivative at x naught, right? That means there's a particular limit, the limit that defines the derivative that exists, and we can write that down. So we know that the limit as x approaches x naught of f of x minus f of x naught over x minus x naught. This exists. This is equal to f prime x naught, which is some finite value. True? We believe this? All right, if this limit exists, what happens? Well, it doesn't mean we can plug x equals x naught into this thing here, right? That's not how limits work. What that means is that if x is very close to x naught, arbitrarily close, then this quotient here is going to be defined, and it's going to be pretty close to this value, right? That's not quite the precise way of saying it, but that's essentially what this means. Certainly, it means that if x is sufficiently close to x naught, this quotient here is defined. It exists. So for x sufficiently close to x naught, but not equal to x naught, right? Because we can't plug a 0 into the denominator. This thing exists. All right, what do I want? I want to show the f itself is continuous. So I want to look at the function f of x itself and see what happens to it as x gets close to x naught, right? And we're hoping as x gets close to x naught, f of x approaches f of x naught. That would be continuity. So we need to look at f of x itself when we're close to x naught. Okay, so what I'm going to try to do is take this expression here that I know a little bit about. At least I know that it exists and I know that what its limit is. And we're going to try to relate it to f of x itself. All right, so what do I have to do to this expression here to try to extract an f of x out of it? This is like high school algebra. I need to multiply by the denominator, first of all. Exactly. It's not a trick question. All I'm saying is I know my goal is to learn something about f of x, and I know that this is currently the only thing I know anything about. So let's multiply by the denominator. That's a good start. Okay, so now I have f of x minus f of x naught. I better add that f of x naught back on. True? I haven't done anything sneaky here. All I've done is solve for f of x. OK, this is good. So if x is close to x naught, sufficiently close to x naught, of course, this term is always defined. This term we know is always defined because we know it has a limit. And this, well, this doesn't depend on x at all. This is just a constant. So what I want, I'm trying to show that f is continuous at x naught. And we know that if f is continuous at x naught, then the limit of this should be equal to f of x naught. So what I really want to do is take the limit of this thing and see what it is. Check what it is. Okay, so let's take the limit. So the limit as x approaches x naught of f of x is going to be, okay, this is exactly equal to this. So it's just the limit of the right-hand side. The limit as x approaches x naught of all of this stuff. X minus x naught, f of x minus f of x naught over x minus x naught plus f of x naught. Now, the good news is we know a little bit about limits, right? This isn't just a complicated expression we have to evaluate. It's a complicated expression made up of much simpler expressions. And we know, okay, this has a well-defined limit. This has a well-defined limit. This has a well-defined limit. That means we're allowed to break these things up. So I can rewrite this as the limit as x approaches x naught of x minus x naught times the limit as x approaches x naught of this whole quotient plus the limit as x approaches x naught of f of x naught. And this works since the component limits exist and are finite. All right, this is obviously 0, right? There's no trick there. What is this limit equal to? F prime, right. All right, f prime of x naught is some number. I don't know what it is, but it's some finite number, right? This is a well-defined number times 0. Okay, this thing is just a constant, right? So its limit is itself. So if I simplify this down, I'm going to have 0 times some finite number. This is f of x naught. And this is looking pretty good. It looks to me as though we've just written down the definition of continuity. The definition of continuity is that the limit of this function as x goes to x naught is equal to the value of the function at x naught, right? This is exactly what we wanted, right? That's exactly why we wrote down this limit in the first place, because we were hoping to show that. So then I can say, indeed, f is continuous at x naught. Right? So if you have a function, you know it's differentiable, you automatically know it's continuous. Other way around, no, but this way we've always got. Questions on this proof or this result? Okay, so now we can build up derivatives of many different functions. Okay, I'm going to probably do one here and maybe post one more complicated one on Moodle because I don't want to spend all our time rederiving formulas from Calculus 1. But for example, if I take f of x equals x to the n, where n is some natural number, some positive integer. Okay, we know we need to look at this quotient if we're going to compute its derivative. Right, so we need x to the n minus x naught to the n over x minus x naught. And a little bit of factoring is going to be in order here. Okay, so I'm going to keep this denominator out here. I'm going to try to factor an x minus x naught out of the numerator. So I tried to factor it out. Now what do I need? I need an x to the n minus 1 to get this leading term. But then when I multiply it with this, I get a minus x naught x to the n minus 1. That's no good, so I need to add something back that will get rid of that. So I'm going to try to add something back that will get rid of that. I'm going to add plus x naught x to the n minus 2. Right? When I multiply that out, this times this and this times this are the same. Right? Again, then I introduce a new term that I don't want, and we can keep running down the list here. Keep increasing the power of this guy, decreasing the power of this guy. So we're going to get, at the end of the day, an x times x naught to the n minus 2. And then that one goes away, and we get an x naught to the n minus 1. Right, so this term times this gives me my x to the n. This term times this gives me my minus x naught to the n. And then we're going to have cross terms all the way through that keep canceling each other. OK, so this is a simpler expression. It's not simpler expression. It's a factored expression for what I started with. It's a longer expression, but it has one useful property in that we've factored out this x minus x naught. So as long as x is not equal to x naught, if we're just close, that's going to make life easier. So if I now try to compute f prime of x naught, that's the limit of this whole thing. OK, so what's going to happen? This and this cancel. All right, then all we've got here is a polynomial, right? It's a beautiful continuous object. And we know we're just going to be able to plug in the value of x naught. So what am I going to get? X naught to the n minus 1 plus x naught times x naught to the n minus 2. X naught times x naught to the n minus 2 plus x naught to the n minus 1. All right, so these terms are actually all the same, right? X naught to the n minus 1. This is x naught to the n minus 1 all the way through. We just have to figure out how many of them there are. So if we go to try to figure out how many of them there are, well, let's see. Here is x to the n minus 1, x to the n minus 2, x to the n minus 3, all the way down to x to the 0. Right? So we have one corresponding to x to the 0th power, x to the 1th power, x to the 2th power, all the way up to x to the n minus 1st power. Right? So how many terms are there? There's n, because we started counting at 0, and also because you know what the answer is supposed to be. Right? So there's n of these, so this is n x naught to the n minus 1. Right? And again, we've worked this out once. We don't have to work it out again. We can use it now. And happily, it's the same result that you were expecting to get. I'm not going to do this calculation here because it's like 2 pages long or something. But I think it's instructive just to see that we can actually get formulas for more complicated things. So this one, I think I will post the calculation on Moodle just so you can see something more complicated. So f of x equals sine of x. You're not simply factoring out an x minus x naught in this case. You have to do a little bit more work, a little bit of geometry. But you can use this definition of a limit to actually come up with the derivative, which should be cosine of x. So this I will post to Moodle. Because I think it's nice to see that these are actually calculations that can be done and have been done. And it wasn't just a lucky guess. We happy with this? The definition of the limit you've seen before. The definition of the derivative you've seen before, of course. I will say, like on problems, if you're asked to do things using the definition, that means you go back to that definition, that thing where I said definition. This is what a derivative is, and you compute that limit. So if I say, show that the derivative of this function is equal to that using the definition, you compute that limit. If I just say, do something and don't tell you what method to use, then do whatever's easiest. Same deal with limits, right? If I say, compute this limit using the definition, I want to see epsilons and deltas. If I just say, compute it, then you can do what you like. And I recommend the simpler option, typically. OK, and similarly, just like we did with continuity, we can combine functions and get new rules for computing derivatives. Because again, we can build up very complicated functions, right? We had that sine of the square root of whatever rational expression. And OK, you could take that and try to do a limit directly, and it would be messy and complicated. Or we could try to build up some simple rules that let us do very complicated things with not that much work. So if we want to combine functions, if f and g are differentiable at some point x naught, and k is a constant. Then we have a few new rules. F plus or minus g prime. So if I take the two functions and add them together to get a new function, and I take the derivative of this new function, well, I could have done the derivatives first and then added these together. So f prime of x naught plus or minus g prime of x naught I could take a function and multiply it by a constant to get a new function. And I say I have my new function, I want to take its derivative. Well, I can simply take the constant out and multiply by the derivative of my original function. And the last sort of simple combination I can do is multiplication. Again, I take f and g, I multiply them together, I get a new function. I want the derivative of this new function. And I get something more complicated than what happened here, right? I don't just take the derivatives and multiply them together. But in this case, I'm going to need to do my full product rule. So they each get their turn to have their input into what the derivative should be. And I'm not going to write the quotient rule that they make you learn in first year calculus because nobody actually uses the quotient rule in real life. Quotients are just products, right? F over g is the same as f times 1 over g. Use the product rule, and it's one less thing to have to memorize. If you want to use the quotient rule, I won't stop you, but I am not going to use it. Okay, again, I'm not going to prove all of these, but let's prove the product rule because that's the most interesting one. Proof of the product rule. All right, so what we wanted to compute, I'm going to start with the left-hand side, f times g, derivative of that at x naught. And of course, if f and g are complicated functions, then f times g becomes even more complicated, and you don't probably want to do this limit from scratch. Okay, but we're going to do it from scratch once, and then hopefully never have to do it from scratch again. So we want the limit as x goes to x naught of, okay, this whole function evaluated at x, so f of x, g of x, minus the whole function evaluated at x naught, divided by x minus x naught. And then we're going to try to manipulate this into something useful, into something that lets us use things we know. Things that we know are, okay, we know that f prime and g prime we can compute easily, right? We'd like a rule that depends on f prime and g prime. Okay, so I'm going to manipulate this expression with that goal in mind. Then I want to get something that looks like f prime or g prime because those are things I potentially know. So we use the powerful mathematical tool of taking an expression and adding 0 to it. Okay, so I start with something like this. I have f of x times g of x. What I'd really love is something that looks like a derivative of g. If I'm going to have a derivative of g, I need something that looks like g of x minus g of x naught. Right? So I'm just going to happily insert what I want into this expression. I can do that as long as I balance this out somewhere else. I've just subtracted an f of x times a g of x naught. I did it not randomly, not for no reason, because I know I want terms like this popping up, but I better add it back on. Okay, so I'm going to have to add back on g of x naught times f of x. Right, so I didn't change anything there. I just added 0 to the expression, and I wrote 0 in a slightly clever way. And we still have this term we better include. It also includes a g of x naught and a minus f of x naught. And quotient, the denominator, I'm going to leave unchanged. All right, again, I've broken this up in terms of simple things that have limits, right? So we know g of x minus g of x naught over x minus x naught, that has a limit. F of x has a limit because it's differentiable. It must be continuous. It must have a limit. So straight away, I can break this up, right? The limit of f of x times the limit of this quotient plus the limit of g of x naught times the limit of this quotient. Again, this works because all these component limits exist. F is differentiable. That means it's continuous, right? We had this one-way theorem. Differentiable, that means continuous. That means we know this limit is f of x naught. This is g prime of x naught. We know that exists. This is a constant, so it just stays the same. And then f prime of x naught, and we know that exists. Right? So it's just using our simpler rules or simpler building blocks to build up a result. So that's the product rule. The other big rule that we'll get to next time is the chain rule, and then start looking at some other properties of differentiable functions.